its reactions. But the most basic spectroscopic analysis of the sequences of compounds found in most biological entities show that these compounds are made specifically from 21 elements, and not just 4 or 5 elements. Where calcium, carbon, chlorine, cobalt, copper, fluorine, hydrogen, iodine, iron, magnesium, manganese, molybdenum, nitrogen, oxygen, phosphorus, potassium, selenium, sodium, sulfur, and zinc are regarded as the 21 elements that are essential for life. However, this number could be further reduced down to 11 if only the elements essential for the human body were being considered, or down to 6 or 5 if only the most basic amino acids, fatty acids and nucleic acids were being considered. Which means that the planet would only need to get those specific elements trapped within pockets and supplied with energy, as this would allow various combinations and permutations to form chemical bonds without immediately overheating and decomposing back to their individual inorganic or elemental components, which would allow them to remain stable long enough to undergo polymerization to become a part of even more complex chains, or to become proteins and lipids, and all of this would mark the start of the very first sign of biocoherency within the planet's structure. Furthermore, it's within these partially closed and intricately linked rock cavities or chemical loops that many of the reactants for most of the newer reactions would simply be the organic compounds, or the strings of organic chemical information, that were manufactured or synthesized in the previous reactions, only days earlier, minutes earlier, or microseconds earlier, within that same pocket, chamber or rock cavity, in the presence of certain mineral phosphates and sulfates that would serve as natural catalyst for the full gamut of organic reactions unfolding. So, the partially closed and/or interconnected reaction chambers deep within the Earth's crust that were able to successfully accelerate and sustain or prolong their synthesis of organic compounds, through the use of chemical ions, thermal energy from the planet's core, and aided by significant assistance from catalytic compounds or minerals, would in a broader sense represent the first true self-contained chemical mixtures and ecosystems of carbon-based chemical compounds on Earth, inclusive of monomers, polymers, sugars, alcohols, hydrocarbons, fatty acids, amino acids, nucleic acids, and so on. As such, within those moments, when the emergence of the first set of protein molecules are attained through those means, then this also would mark the arrival of the first set of enzymes, as well. This is because most enzymes are just proteins that, in perpetuity, attract, unlock, store or retain the chemical ingredients, reaction sequences, or catalytic pathways for ever more complex polymer chains to be synthesized or manufactured, and allow more chemical information and chemical energy to be stored for increasingly more complex chemical mixtures and chemical systems. In essence, these newly formed enzymes would be able to act as natural catalysts, or extremozyme, and thus would help many complex reactions to occur at much lower activation energy levels than they otherwise would in nature, as enzymes are known to be able to catalyze more than 5,000 biochemical reaction types, even at extreme temperatures. As such, the first emergence of life and biological complexity would not only be about the quality and quantity of chemical ingredients, but it would also be about energy availability, reaction activation levels, chemical durability, and catalytic integrity, as well. All of which would be present even as deep as 4 to 7 miles deep within the planet's crust, according to the findings of the Kola superdeep borehole located in Russia. Where one of the more intriguing discoveries made within the Kola superdeep borehole was the detection of microscopic fossilized plankton some 4 miles down. These findings were seen as significant because usually fossils are found in mainly limestone and silica layers much closer to the surface, but these microscopic fossils were found encased in organic compounds that remained chemically stable and fully intact despite the extreme pressures and temperatures of the surrounding rocks, which ought to have thermally decomposed those compounds, specifically, back into inorganic compounds, or at least turn them into petroleum, crude oil, or hydrocarbons. Beyond this, the findings of the Kola superdeep borehole doesn't only present a new outlook on the way the Urey-Miller experiment should have been conducted, but it also confirms that the Earth's interior possesses a significantly higher level of free, or loose, hydrogen, as suggested in the model that states that the planet's core is capable of producing and performing nuclear knockout reactions, or forcing frictional collision amongst naked atomic nuclei, and inducing isotopic decay. This is because another unexpected discovery, at various stages, within the Kola superdeep borehole expedition was the large quantities of hydrogen gas that escaped as they dug the hole. The drilling mud that flowed out of the hole was described as boiling with hydrogen. However, this should not have been the case, as most of the accepted models, regarding the overall structural formation of the planet, point to the notion that most, if not all, of the planet's hydrogen should have evaporated away into space when the planet was super hot, was being bombarded by meteors and asteroids, or was in a fully molten state, billions of years ago. So, the findings from the Kola superdeep borehole points to the possibility that the planet most likely has a natural geothermal, or thermodynamic, mechanism, deep within its interior, that has somehow produced an excessive amount of freed hydrogen atoms and/or isotopes. Because what are hydrogen atoms if not just individual protons, or proton-neutron pairs, that regain some electrons to become stable atoms? Consequently, it is only at those depths that are comparable to the superdeep borehole where there would be enough energy, along with pockets or cavities filled with the many gaseous atoms, ions and isotopes, especially of hydrogen, that would be needed for the emergence of the first set of simple enzymes, or natural organic catalyst, that would facilitate the creation of the very first closed-loop autocatalytic chemical mixtures. Such that, these chemical mixtures or chemical systems would conduct organic chain reactions on overdrive, as the chemicals contained within them would be either the main ingredients and/or the means of lowering the activation energy for future reactions, which would exponentially increase the likelihood of specific types of reactions taking place, or being directed to converge or diverge in particular ways. Essentially, these mixtures would contain both the reactant and catalysts that were synthesized by and/or within the mixture itself, as enzymes are the type of organic compounds or polymers that can catalyze the production of other organic molecules. Additionally, the existence of these catalyst-filled mixtures that are running on reaction autopilot would facilitate, or allow, ever more complex polymer chains to be synthesized, or manufactured, within minutes if not microseconds after each other, which would make them appear almost as if they were organic chain reactions. Importantly, this would allow vast quantities of chemical information, or chemical energy, to be stored within these increasingly complex compounds, or chemical systems. Therefore, the constituent parts, or catalytic substances and substrates, within these dynamic mixtures would quickly evolve to create or synthesize more complex and larger polymer structures, which would allow them to acquire more functionalities, as well as more physical properties, traits, and shapes. After that, the first set of organic molecules, or polymers, with the catalytic properties to attract, optimize, recall and/or preserve the exact steps, ingredients, and/or components needed for the production of special and/or complex organic compounds, such as proteins, would serve as the first type of genetic code, and would serve as a means of storing the chemical and catalytic identity of the mixture that they are enclosed in. In addition to this, the emergence of lipids, which are the complex polymer chains, or molecular chains, of fatty acids, would represent the emergence of the very first partially insoluble molecular shells or membranes, that could enclose or wall off parts of these mixtures, which would allow some catalytic systems to develop new and/or unique identities, as they begin to make or synthesize new compounds, even while being in the same solution or same pockets as others. Thus, the many little insoluble spherical pockets or oily bubbles created by these lipid molecular shells would serve as the very first maze-like multi-chambered, or multi-layered, miniature structures that could fully enclose and insulate various chemical systems, or mixtures, of ongoing molecular reactions, and strategically allow them to maintain their separation from all other ongoing reactions involving other catalytic enzymes and proteins, or from all outside or environmental stimuli. Consequently, the concurrent emergence of the carbon-containing compounds, or chemicals, known as proteins, enzymes, and lipids, along with any means of molecular chemical information storage, would mark the point where some of these organic molecular systems would represent fully functional sequences, or pockets of chemical information, and they would preserve the accumulated lineage of the chemical information, properties, functionalities, chemical pathways, rules, protocols, syntax and/or chemical signatures, unique to the systems or mixtures that they came from. As such, these new and/or ever-changing units or pockets of biological and chemical coherency would exist ostensibly as an enclosed set of localized mixtures, or as a web of compounds, that exist collectively to follow an existential set of chemical rules, written in and/or stored in carbon-based compounds. Therefore, within these now lipid-enclosed chemical pockets, reactions that once took days, or even millions of years to unfold within deep underground natural cavities, would now reach completion within microseconds, and this jump in complexity and efficiency would result in the creation of ever more complex chemical entities, using strictly energy from the planet's interior, and these new systems, mixtures or floating pockets of organic chemical compounds or polymers would directly straddle the line between the living and non-living world.